Yeah, thank you. Dean was really upset not to be here, but we're happy to have his content. I was going to summon my best Dean, put on some glasses, and put on a wig with gray hair, which is a lot funnier when I didn't have gray hair. So I hope I can fill the part and fill Dean's big shoes. So what he wanted to talk about today was some work that I was on along with a host of others that we did about 5, 6, 7 years ago now, basically comparing remote sensing and field-based geologic maps and what that means for Artemis. Next slide. So the origin of this project, as he's noting here, is that for Desert Rats 2010, which was a 2 kind of pressurized rover simulation that went from Black Point lava flow in the San Francisco volcanic field all the way over to Colton Crater. The traverses were intended to simulate Apollo-style geologic exploration. That is, there were stations that were planned. They would roll up to different sites. They would do EVA from the rovers, and they would take samples and then get back into the rover and move to different locations. This was a multi-day effort. The crews were interacting with science support as well as a flight control room that were based in the field. There was a strategic team that was slated for overnight discussion. And so it was a lot of things that we were doing, kind of a precursor for what Kelsey was talking about with Jet 3 and Jet 5. Really interesting work, and some of the things that we were recognizing there as far as like the observations that were made in the field and the pre-mission map and how that aligns with the observations that were taken in the field, both as samples and going in the field and doing mapping. Next slide. So just like Kelsey was saying, we had a pre-mission map that was generated by some folks at the USGS, and this map was used to help identify the routes and the stations, along with a host of other things. I should point out that, geologic maps are not the solution to everything, and so we're not here trying to advocate that as being like the one solution. It's just a part of the critical component in the architecture that needs to be considered when we're doing these station plans and traverse routes. So for DRATS 2010, we had this pre-mission map. It was based on a 0.5 meter ortho image, a 1.5 meter DEM. When he says Apollo methodology, what he's saying is that we were doing remote mapping. We were trying to identify the context of the three-dimensionality of these units, and then get enough information there so that the mission planners and task could start to slate out the traverses and identify valid locations for sampling. Next slide. So this is the box. This is SP Crater. You can see SP Crater and SP Flow moving off to the north. So the red box is actually oriented north-south, and so the straight lines are pointing to the north. So this is an oblique image looking to the northwest. But what you can see here are 2 different traverse routes for these quote-unquote pressurized rovers. That's teal line and the yellow line. You can see how they're interacting together. There's a lot of power in having 2 different crews out there. They can stay line of sight and still communicate and make kind of expanded observations. And this is also the area that we still do some training. And so it's an area that we've leveraged quite heavily and are paying attention to. Next slide. So what happened was, after we made the observations for DRAT 2010, there were some teaching components that that Dean and some others were doing out there. And what they were realizing is that a lot of the things that the samples were taken did not align necessarily or align exactly with what the interpretations was. This prompted a comparison of these pre-SIN and post-mission geologic maps, and especially what it means to do field mapping. So what we want to know is, like, how right can we get these maps when we're doing things remotely? And he says down the end is, what we're asking is, did Apollo get it right? Meaning that, where are we missing observations? Where do we need to improve our processes? And it's important to understand too that a lot of these questions that Dean is pitching here and that we answer by going in the field are still being assessed through these JET exercises. It's really helpful to see, like, what are they observing and what can we do better from a planning standpoint to make sure that they're maximizing these observations while they're reducing risk. Next slide. So the project methodology basically is, we had a bunch of samples that were taken from DRATS. What if we took those samples and had a team that was assessing just those samples and augmenting and refining the pre-mission map using those samples alone? It's basically the Apollo methodology. You make a geologic map, you plan out traverses, you take samples, make observations in the field, and then you take those samples and all of those kind of crew notes and observations, and you refine the geologic map. And then what if you also sent a crew out that was not restricted by any kind of like slope or anything else, and they could just tromp around in the field, basically making a terrestrial geologic map? Now you have 3 geologic maps, a pre-mission map, a post-mission map that is augmented and refined by the observations that were made in the field, and then what is essentially the control, what we would see if we went out in the field and were able to get all over the place. It's important to note too that that last component, doing the field work, does not account for the lab simulations that the lab team would be able to do. So they were able to get information that we wouldn't be able to get in the field because they had the capability of analyzing these things. So 3 different maps, and how well do they align? And when they're not aligning, why are they not aligning? Next slide. So the laboratory team activity, they follow a process similar to what was done after each Apollo mission. Crew members had field data, backpack information, location information. They took samples. So handling is an examination of all the samples. He's noting here, as well as the geologic context, where those samples were taken, just like Kelsey was just talking about, as far as sampling and where the samples were in relation to the geologic map and how that lined up. And also geology and geomorphology was analyzed using the data set. So anything that was available to them that was pre-mission as well as post-mission kind of samples and field crew and observations. Next slide. This looks compared to the field team activity, which I already noted was conducted in standard geologic mapping exercises, determine the number of flow units, determine the number of vents, determine the number of sedimentary units that were out there, and also characterize the mantling deposits. These mantling deposits tend to be really important, especially for lunar exploration, because what we're going to see there is going to be lunar regolith. And so understanding how we can identify and characterize and differentiate some of these units is going to be really important. So the primary map area was 1 to 24,000 scale, and we spent about 8 days in the field, and this was in June 2013. Next slide. So this is the laboratory team geologic map, the geologic map that they came up with. And so what they're identifying is a single limestone base unit, multiple basalt and basaltic andesite units. That's something that they can say that we would never be able to say from remote data sets. I mean, if we had composition, we could get bulk chemistry and we could say this is basaltic, but we would never be able to say what kinds of crystals were in it, and therefore we could never get at really some of the processes that we're in placing. Some bulk characteristics, sure, but as far as the nuanced details, we can't do remotely, and we need samples. Phenocryst assemblages for B1, B2, B3, B4, B5, that's basalt 1 through basalt 5, identifying different units. Also identifying the characteristics of the cinder cone units, the size of these things, the distribution of them as they're rolling down the hills, and then surficial units, as I already talked about. Next slide. And then the field team geologic map. So mapping 2 vents, multiple lava flows. The crystal assemblage for a lot of these were very similar, and so differentiating them, we had internal contacts, basically differentiating 2 contacts, 2 units that we thought were very similar, and so that's where you see that kind of pink unit. We can differentiate flows, but we cannot always differentiate whether they're unique flows or one part of a kind of one single event. We identified at least 4 major units, and then getting into surficial units and how to differentiate surficial units. What you're seeing here is that surficial units are really hard to differentiate. So in all 3 maps, there's maybe 1 or 2 different units, and that's a focal point of what we're doing moving forward, especially for Jet 5. Next slide.
Just under 2 minutes.
Gotcha, thank you. So this is a comparison. I encourage everybody to go back through and look at these different comparisons. You can see where things are right and wrong, and every single one of these maps is varying from the other one. So there are differences, particularly when interpreting the number of volcanic units, but the main differences are driven by being able to go into the field and access areas that we weren't able to before. Next slide. So what Dean is getting at here is that the Apollo style, creating a pre-mission geologic map and then verifying it, is largely correct. This means that our exploration plans are correct and good. It just means that we need to keep refining our understanding. And Kelsey Preisel just had a really good quote. I love it when people are quoting the crew notes from Apollo and saying what could be done better for the geologic maps. And so there are things that we can certainly be doing better. So expect critical detail to be discovered by the crew, obviously, and expect those geologic maps to change. And that's a good thing, right? Making changes to the maps is not a bad thing. It means that the process is working. Next slide. So this is kind of the crux to me of this talk, is this little curve here, what we know versus time. And so what happens is that we come up that curve really quickly when we're making observations. And then at some point we kind of bend over, and then it gets more asymptotic to time. So the evolution of what we know through time is kind of diminished. And so he's plotting here kind of where he thinks this pre-mission and post-mission knowledge is. And then this study is the field-based knowledge. So the science capture is something that's important that we need to be really attending to. And I think that we're getting there with a lot of the exploration tasks that we've done and with what Apollo has done. Next slide. So conclusions, I'll let that be there for you. Yeah, thank you. I think that we have a lot of things going on, and the geologic mapping parts as far as field comparisons has been a really relevant part of this discussion, and we hope to continue that. Thanks.